starts by asking what is meant by the convolution theorem, and actually I recapped on this just as we were going through the topic map earlier. So just to recap then, the convolution theorem is stating that if we take an image and a filter, or kernel if you want to call it that, and we transform both of those independently into the frequency domain, then we can just multiply those frequency domain representations together to produce another frequency domain representation, and then by taking the inverse Fourier transform of that representation to resynthesize an image, if you like, then that process is a convolution, and equivalent to performing a spatial convolution by sweeping that filter over the image, doing that place-for-place multiplication in every position. So if you think about it, taking if you have a very large image that's maybe many millions of pixels, and at every location you are performing one of these place-for-place multiplications with a filter where you're multiplying all the values in the filter with all the image pixels underneath it, summing them up and writing the value out, then what you've got there is a process that is n times m complex, where n, let's say, is the number of pixels in the image, and m is the number of pixels in the filter. Okay, so in general we would say that's an n squared complex problem of the order n squared. But if you take the same images and you transform them into the frequency domain, which can be done using something like the fast Fourier transform, which is log n complex, then what you have is n multiplications in the frequency domain, so your process is n log n, or n log n complex, which is a lot faster than an n squared complex calculation. So the upshot is that for large images, performing convolution in the frequency domain is a lot faster, and any photo processing package is basically doing that. No one's actually coding up a loop to do this sweeping of an image over the image, a filter over the image. So the practical implication of the convolution theorem, or one of them, is that it's faster if you do the convolution in the frequency domain. The other practical implication is, as I say before, it gives us a way to explain the behavior of certain filters. So, for example, we can talk about why a Gaussian blur gives us fewer artifacts than a box blur. Well, the reason for that is that a Gaussian filter, a Gaussian function, when transferred into the frequency domain via the Fourier transform, is represented by a Gaussian function in the frequency domain. If I have a Gaussian of standard deviation sigma in the spatial domain, and I pass it through a Fourier transform, then you can write down the equation and just run it through the maths yourself. You'll see you end up with the equation for a Gaussian with a standard deviation that is 1 over sigma. So it's still a Gaussian. So it's an infinite function, but it's a function that is entirely positive and attenuates smoothly as it gets to infinity. Whereas if I take a function like a box function, which is basically an impulse function. So an impulse function, or Dirac function, is a function that is 0 everywhere and some positive value at just one location in the spatial domain. Box function is basically like an extended version of that, that's positive at just several locations, contiguous locations in the spatial domain. Then when we transfer that into the frequency domain, what we see is that we have a sinc function, which is basically sine x over x. Okay, and that function is peaking around 0 and is attenuating towards 0 at infinity, just like a Gaussian, but it undulates between the positive and negative regions of that frequency space as it approaches 0. And what that means is that we are boosting and attenuating alternately frequency bands in the image, which gives us that ringing effect around high frequency artifacts in the image. Anyway, I'll go into more detail than is necessary to answer this question, but the other practical implication is that we can understand a little bit more by considering the convolution theorem why we see the kinds of artifacts we see when convolving with certain filters. Okay, any questions on that? Okay, right. Well, the next question actually we already answered while we were talking through one of the previous ones, which is to describe the operation of the ReLU layer and the role that it plays in enabling CNNs to learn complex functions. So I think we've already talked about this before, briefly. operation of ReLU layer is it's a nonlinear transform that clamps negative values to 0, and by introducing that nonlinearity enables CNNs to learn more complex functions because successive convolution layers are separated by nonlinearity and don't collapse to a single convolution. So this is therefore allowing the network to be deep. Okay, C. Increasing the depth of a neural network can increase its power, i.e. ability to learn complex functions. What is meant by the gradient vanishing problem, and explain its implications for training very deep networks. So again, did touch on this discussion before, talking about how in a deep neural network it's difficult to propagate gradients back to update earlier layers in the network if the network is very deep. This causes the gradient to vanish and makes it very difficult to train deep networks from scratch. For each of the following networks, explain how the gradient vanishing problem is dealt with. Okay, we've talked already about GoogleNet. The way it's dealt with is by adding auxiliary loss functions so that they're effectively like a signal booster, if you like, to the gradients by injecting them directly into middle and early stages of the network. How about these two networks we haven't recapped today? Residual networks. What is a residual network or a ResNet? Can anyone remind me of what the structure of a ResNet looks like? What kind of network is a ResNet? Right, so if you remember, a ResNet is an example of a fully convolutional network, okay? Because it only has convolutional stages in it. It doesn't have any max pooling or dropout. So therefore, it has a lot of convolutional stages in it to reduce that image as it passes through the network. And in fact, a ResNet is made up of just many convolutional stages that are 3x3 filter stages. Okay, so it's a very long network, many layers. There are different configurations of it, like ResNet 50, ResNet 152, 152 layers. Okay, so these are examples of very deep networks that have to deal with gradient vanishing problem. So what is the design feature of a ResNet that helps it do that? Yeah, absolutely, thank you. Yeah, skip connections, yeah. What are called in the context of ResNet residual connections, but basically they're skip connections, okay? So with the skip connection, what we're doing is actually bridging across pairs of convolutional layers, okay? And then what we're doing is we're taking, if I've got two convolutional layers, we're bridging just like this, and and these of course have come from other convolutional layers as well. We're creating a skip connection down here and adding in channels from here to channels here. There are two different ways of concatenating, of adding in the channels. We can either concatenate them to make extra channels, or we can just add, like arithmetic add to channels that already exist there. And by creating these connections, we allow gradients to propagate further down in the network. Okay, so that's ResNet. And then highway networks are a very similar idea that were introduced at the same time, but didn't really gain popularity, I guess because they're slightly more complicated. All we have is a similar kind of arrangement, but we have a learnable parameter here. Okay, and that learnable parameter acts like a gate. Okay. As to whether to let that residual information feed into successive stages in the network, okay? And the weight is to what degree, that the data gets scaled before being added into the network. So these are just different ways of propagating forward gradients to mitigate the gradient vanishing problem. Okay, so part D, compare and contrast two common forms of Siamese network and explain how these may be trained to learn a feature embedding from images. You should ensure you describe the architecture, the loss function, and the training methodology for both forms of network. Okay, so what is meant by a Siamese network? Does anyone remember?
Parallel network shared weights.
Absolutely, yeah. It is a multi-branch network that shares its weights. So what does that look like? Well, usually, if we're using a Siamese network to learn a feature embedding from images, we're going to have CNNs for those branches. So we have an image that's going in to a branch, and it is then passing through successive convolutional layers probably through some sort of some backbone that resembles a classification network, like an AlexNet or GoogleNet backbone would be used, ultimately resulting in some sort of fully connected layer. Okay, and if it's a Siamese network, there would be multiple branches. So we would have perhaps another branch, perhaps even another one. So we looked at two kinds of Siamese network to answer part of this question. We looked at what's called a contrastive loss network. We also looked at a triplet network. Okay, so let's look at the triplet network as an example. Okay, so here we have a triplet network which has three branches. Those branches involve taking in an image. We're going to call those A, P, and N for the anchor, the positive, and the negative branches of that image, of that network, sorry. Okay, the image is getting fed in to a backbone of some kind, like it might be GoogleNet, Inception or something like that. Okay, it's going into a fully connected layer at the end of that, and then what we would usually do is, well, actually, you know what? Let's. There are different ways of drawing this. Let's draw this in a more intuitive way. Yeah, let's just. You know what? Let's just keep it like this. Okay. As was correctly said, the weights in these branches are shared if it's a Siamese network. So although it looks like we're learning three different sets of weights, in fact, the optimization is rigged up such that there's only one set of weights that is serving for all of the branches. So we'd usually indicate that with some arrows to indicate that the weights are being shared, okay, and equally so across the fully connected layer. So what that means is this is learning a function that takes in an image and basically maps that image to a point in a high-dimensional space via the activations of the fully connected layer, and that then is the feature embedding that's being learned. So this might be, something like 128-dimensional or 100-dimensional. This would be, an image that would go into a standard backbone. So if this is GoogleNet, it would be like 256 by 256, something like this. Okay. So that's our anchor branch. That's our positive branch. That's our negative branch. Let's call the output of this A, P, and N. Let's call these inputs to be a bit clearer. Let's call these image subscript P and N. Then what we want is to learn this 128-dimensional embedding such that the anchor and the positive are very close together, and the anchor and the negative are very far apart. Yeah? So to train this network, what we do is we present triplets of training data to it. What we would have is an anchor would be an image, a positive example would be an image that's very similar to the anchor, and a negative image would be an image that is dissimilar to the anchor. And it's up to us to define what we mean by similar or dissimilar. Yeah? So if I was building a visual search system, which is one application of this kind of network, then what I might do is I might collect together images that I consider to be very similar and very dissimilar and train the network using those under some definitions. So, I've used this kind of network before to train Siamese networks that are good for visual search based on style. So I'd collect together triplets of images where two of those images had a very similar visual style, and the negative image, had a dissimilar style, and train the network with that so it could learn a definition of visual aesthetics. But equally, you could define these as being images that contain the same kind of object and a different kind of object. It really depends what you want your feature embedding to represent and encode similarity as. Yeah. Okay. So in order to figure out what the loss function for this network should look like, we have to understand that we should penalize differences between the anchor and the positive, and encourage differences between the anchor and the negative. So what we want is, if we've got the difference between anchor and negative in that space, right? We want big values to be good. So if this is a loss function, we want to negate that. Yeah? And we want to encourage and we want to discourage small values here. So this would be our loss function, but we also have what we call a margin that we introduce as well. Pull that up. So if this is our loss function defined between that triplet, okay, what we're going to do is introduce just a final wrapper around it that says what I'm interested in is the maximum of let's see, 0, m plus this. So this is our loss function. So what this is saying is I want a loss function that is the greater of this quantity or 0, so I want a non-negative loss, and this loss function that I defined, I'm just going to add a constant value m to, which I call the margin, and the purpose of the margin is to encourage convergence and get us away from a situation where A, P and N all collapse to the same location in the space. Okay, so the m in practice guarantees that the n is at least m away from the anchor, to prevent that collapsing of A, P and N to the same point in the space during training. Okay? So that is a triplet loss network. I mean, sometimes people draw this, and this is what I nearly did at the beginning, sometimes people draw this as a big, long, fully connected layer that unifies the branches, which is sort of more comfortable to draw because it shows the network converging to a point, but actually it's just equivalent to just writing drawing the fully connected network with this notation that indicates the weights are the same. Yeah? Does that make sense? So the network is learning a single function that maps images to points in a search embedding. Okay. Which then could be used for visual search. The other example that we looked at was the contrastive loss network, which is the Siamese network that just has 2 branches. So basically it's just this diagram but without the third branch. Okay? But it has a different loss function. Okay, the loss function, oh dear, just considers A and P because we don't have a negative branch, but we present in alternate fashion positive and negative examples to the network. So if I have an anchor image and a positive image, I'm going to feed those both through the network. I'm going to set this constant y to be 0, and then my loss function is going to be 1 minus y, so basically it's going to be, forget this bit in the parenthesis here, it's going to be a minus p, proportional to a minus p. So again, this is just like the triplet loss function I've shown up here, but we're just dealing with the positive part of it. But for the negative part, we're just going to add a term here that's activated only when y is 1, when we've shown a negative example on the right-hand side. If y is 1, then this first term is completely disabled. The second term comes into play, which is basically this a minus p. So this is negative a minus p, which is like the negative term here in the triplet loss function. Yeah? And it has this margin associated with it, just like the triplet loss, that discourages or prevents the negative example point getting too close to the anchor, and prevents that collapse again of the representation. That makes sense? So in this case, we train this network with pairs of data, half of which have positive examples, half of which have negative, and they're presented in mini batches. So you do like a mini batch positive, a mini batch negative, and so on, using a different loss function in each case. Yeah?
For each instance, we have total 3 images, a pair of positive and a pair of negative.
For the triplet network, you have triplets. For the contrastive loss, you just need pairs of images.
But the loss function has the both positive and negative parts, and the positive generated from similar networks and negative from dissimilar.
I don't understand your question. Sorry, say what? Yeah.
If you want to generate a loss,
yeah.
you need 3 images in total, don't you?
No.
No?
Now you need two images, the A and the P, right? So there's only two variables there, yeah? This is your A, this is your P, okay? If your P happens to be a negative image, you set y equals 1 when evaluating this loss. If your P happens to be a positive image, you set y equals 0, yeah. Right, any other questions? Yeah.
What the advantages of one over the other?
Yeah, that's a good question. I mean, it may be that, so it's harder to create triplet data, okay, because for every positive example you need a negative example. That may not be the case, and if it's not, then you use contrastive loss instead. But it can be, it's just anecdotal, but I find it harder to learn a good representation with contrastive loss function. It tends to be, the representation isn't quite what you want. So if you've got the balanced data, you should use a triplet loss. If you don't, then you should use contrastive loss. It's a rule of thumb, I would say. Okay. Okay. Right, question 3. Explain what is meant by aliasing in the context of image sampling. What is the Nyquist limit, and how can it be applied to mitigating the appearance of aliasing when performing image warping? Okay, so this is a question on sampling theory. Who remembers what aliasing is? Yep.
Is that when two dissimilar frequencies mix up because of too long sampling?
It is to do with frequencies mixing up, but that's not quite the definition of aliasing. So what kind of frequencies are getting mixed up in aliasing?
Higher frequencies?
High frequencies, yeah, absolutely. So aliasing occurs when we sample a signal at too low a sampling rate. Okay, so the example I usually give is CDs. Not that probably many people play CDs anymore, but anyway. So CDs, compact discs. The audio on compact discs is sampled. A sampling rate for that is at 44 kilohertz, 44,000 samples per second. Okay, the reason that is set that way is because the highest audible human audible sound is about 22 kilohertz. So we want to sample at least twice that rate, and actually that is what the Nyquist limit is. The Nyquist limit says that we have to sample at least double the rate of the highest frequency component in the signal. Okay, so when people are mastering CDs, recording CDs, the first thing they will do is take the signal, input audio signal, and just filter out anything that is higher than 22 kilohertz in that signal before digitally recording it into the CD, because otherwise those high frequencies will masquerade as lower frequency signals in the image. So taking it back to a visual example that you will have seen in the labs, okay, if I take an image that has a lot of high frequency information in it, like a very, very fine-grained checkerboard, and I resample that image via some image warping approach, so what I might do is I might, for example, take that very, very fine-grained checkerboard pattern, and I might downsize it, possibly having performed some sort of rotation. What you'll find is you get a checkerboard pattern, but it has this kind of wavy appearance across it, where large black and white checks have appeared over the grid. And that is aliasing, but it's just aliasing in 2D instead of 1D. Okay, so why has that happened? Let's have a look. Okay, so let's remind ourselves that when we're doing warping, we have our source image, we have our target image, and to do high quality warping, we're usually doing backward mapping. So if this is our target image, what we're doing is we have our matrix transformation M, which is describing the operation we want to perform on the image, like some sort of affine transformation. Okay, and what we're doing is we are inverse mapping from here, from the result image, to figure out where we land in our source image, right? So I iterate through every pixel in my target image, apply this transform to the point, and figure out where I land. Now, if this image here at the source is very large and contains a high frequency checker pattern, and so on, and this image here is quite small, okay, let's suppose it's a factor of 3 smaller, right, then this point is going to land up here. This point here is going to land up 3, it's going to be 1, 2, 3 squares across, and so on, and so on. So it's going to be very coarsely sampled. Yeah? Now, if this is subject to a rotation as well, what we're going to quickly find is that these coarse samplings of this grid don't correspond to a regular checker pattern, that there's some sort of a distorted checker pattern, and that will happen with a kind of beat frequency, which is the aliasing frequency that induces this coarse scale kind of black and white pattern across the target image. And that's because we're sampling this signal at too low a rate. The lowest rate we should be sampling this signal here that's going that has a wavelength of 2 is we should be sampling at well, let me see. Well, we should be sampling at every pixel at half that rate, but we're not. We're sampling it at much lower rates, which is why we would go aliasing in that scenario. So, what is meant by aliasing in the context of image sampling? It's when we resample an image under some digital image transformation like a warp at too low a rate, possibly because we're changing the scale of the image. Nyquist limit tells us that we need to sample an image at least twice its highest frequency component. So how can we mitigate the appearance, or that means reduce the appearance of aliasing when performing image warping? Well, we have to filter the image first, just like the CDs, the music example I gave, in order to reduce the presence of high frequency content in that image. In practice, what that means is we run a blur over the image to get rid of the input image, in order to get rid of that high frequency information. Okay? Right, any questions on that? All right. Okay, part B. Consider the following grayscale image, I of x, y, where x is ranging 0 to 3 and y is 0 to 3. So we've got a 4x4 pixel image there. Origin's in the top left, and we're representing it by this function I of x, y. Calculate the intensity at location 2.4, 1.6 using each of these interpolation methods: bilinear interpolation and Gaussian interpolation. Okay, so let's have a go. This is a calculation question now, so let's see if we can work it out. I'll do it again on the board. Okay. All right. So, what's helpful to do to draw when we are answering questions like this is a sort of close-up image of the pixels in question. So let's see. We're interested in location 2.4, 1.6. So at 2.4, let's see, we've got that's pixel 0, 1, 0, 1, 2. So we've got pixel 2 here, pixel 3, so x is 2, and then we've got y equals, and that's between 1 and 2. Okay. Now, and then we've got actual values for here. Let's call these pixels A, B, C, and D. The value of pixel A is what? So pixel A is 2, 1, so that is 190. You can see that from the grid. B is what are we at? 3, 1, so that is 180. don't know why I'm writing these in brackets, sorry, no point really, is there? C is 2,2, which is 200. And D is 2,3, so 3,2, sorry, which is 215. Okay, right. Now we're interested in the pixel at 2.4, 1.6. So we're interested in 2.4, 1.6. Okay, which is this pixel here. Let's call that P. That's what we want to know. Okay, so what's the first thing that we do when we calculate, when we're doing a bilinear interpolation? Yeah, so we pick a direction. We're gonna work down. So I mean, okay. It doesn't matter which way we go. Let's go this way. So let's call this point E. This point F. Let's work out what E and F are. Well, E is going to be some blend of A, which is 190, and C, which is 200. Yeah? So E is closer to C than it is to A, so it's going to have a higher weight on the C value. So that is actually going to be 0.6 times C plus 0.4 times A. Can you all see that? Because that distance there is 0.6 away, and that distance there is 0.4 away. That distance there is 0.4 for the next step, and this distance here, 0.6. So F is similarly 0.6 times B, D plus 0.4 times B. Okay? So to calculate P, we're going to need to blend E and F according to these ratios. So P is going to be equal to 0.6 times E plus 0.4 times F. Yeah? See that? So we won't do it now, but you would just substitute the values for C, A, B, C, and D into that and evaluate that and get your answer for P. Okay? Any questions on that? That's the bilinear interpolation. Okay, now how about Gaussian interpolation? So in the Gaussian interpolation, we have a Gaussian that is centered at P, and we're trying to calculate the weights that we need to combine A, B, C, and D by by sampling that Gaussian. Right. So let's imagine that I've centered a two-dimensional Gaussian with its mean, so its center at P. Okay, that Gaussian is infinite in its extent, and we'll be able to sample its height at these 4 points, A, B, C, and D. Okay? So what we're going to do in order to sample that is calculate that distance. Call this distance A, distance B, distance C, distance D. Okay? Right. What is distance A? Anyone know how we're going to calculate that? Thinking about right angled triangles? What would be the equation for distance A? Okay, well, we're just remembering we're interested in 2.4 or 1.6. So we've got a side here which is 0.6, we've got a side here which is 0.4. So what is distance A? Right, thank you. And distance B is going to be 0.6, 0.6. Distance C, 0.4, 0.4. Distance D. Right, so distance D is going to be the same as distance A, yeah? Right, let's work that out. Who wants to work that out for me with a calculator? Shall I do it in Windows Calculator? Do I have to? 0.721. 0.721. Okay, 0.4 times 0.4 times 2 raised to a half. 0.566. Okay, what's left? 0.6 times 2 raised to 0.2. Oh no, I screwed that up, sorry. Times 0.6, that's that. Oh no, Right. Right. 0.849. Okay, so there are distances, and we're going to push those through our Gaussian function. Okay, so in this case we've been given a Gaussian function conveniently, and we're saying that our standard deviation of that Gaussian is going to be 2 is going to be 1. Sorry. So our equation then for our Gaussian is going to be approximated by e to the negative, and in this case we've got a distance. We can just push straight through. In fact, we don't even need to use the two-dimensional Gaussian function here. So we're just going to say it is some x divided by 2 times 2 squared. So it's squared over 4 in this case. That's correct. 2, 1. Oh, sorry. Yeah, over 2. Sorry, you're right. Thank you. Okay. So that's the equation I've chosen to give them there, so that's fine. Okay, we'll use that. Okay, so these are the weights then. We're going to call these WA, WB, WC, WD. Right. Does anyone want to calculate that for me that's got a calculator handy? I don't know if I want to try Windows Calculator for this one, but I'll do it if I have to. Okay, fine. Okay, well, we got 0.721 squared over 4. Oh no, over 2. Sorry, you corrected me. It's negative that. Oh, right, something like that. Okay, and it's the exponent of that. Has he got that? Oh. Oh, okay, I don't know how to use the Windows calculator for e to the power of, so does anyone want to do that for me on their calculator?
3 answers there, right?
Go on then. Thank you.
0.771 for the first one.
0.771.
0.697.
0.697.
0.852.
0.852.
And the last one should be the same.
And that would be the same, 771. Okay, much appreciated. Thank you very much, Matt. Doesn't really matter, just doing a demo. Okay, right. Okay, so now we need to figure out what those what the P was. Okay, so our P is going to be equal to that weight applied to A plus that weight applied to the B weight applied to B plus the C weight applied to C plus the D weight applied to D, and we're going to normalise by WA plus WB plus WC plus WD, and that will be our value of P. So the A was 190, wasn't it? The B was 180, 200 and 215, yeah? So that would be what you evaluate then in order to get your answer for P. Okay. That make sense? Why do we do this? Denominator. Right, well the area under a Gaussian is 1. So, if we sampled infinitely under all our data, we shouldn't need to do this, but we're only sampling at 4 locations. So the sum of our weights will not equal 1. So we have to do that. Or in this case, won't equal, yeah. Okay. Right, part C. You're working on photo editing software and are asked to develop a new feature for seamlessly removing parts of a photo. For each of the 3 use scenarios below, recommend an appropriate algorithm to seamlessly remove parts of the image. Ensure that you describe the operation of the algorithm in detail. Okay, part 1. The user wants to remove unimportant space in a photo. Which algorithm that we've covered on this course will do that? The seam carving algorithm, that's right, absolutely. Right. So do we remember how the seam carving algorithm works? Okay. Let's pull the appropriate slide up. Okay, so here it is. Here's the example. We have an original image, we have space we want to remove, and this is the desired result. Okay. So what we're going to do is measure something for every pixel. We're going to measure how important the pixel is. The way we're going to approximate how important a pixel is by considering how much high-frequency information that pixel has around it. And the way we're going to measure that is using the Sobel edge detector. So we're going to take that image, grayscale it, push it through the Sobel edge detector, calculate the Sobel magnitude, and then we're going to get a map like this, where the grey level of the pixel corresponds to the importance of that pixel. And we're going to try and identify runs of pixels, contiguous runs of pixels from top to bottom of the image that sum up to the least importance if we were to add up all those pixel values as we move through the scene. So in this case, the pixel seams in red are ones that we consider to be good decisions. We'd like to remove those seams. And the purple one is an example of a bad seam. And when I say remove a seam, what I mean is we identify this run of pixels, and then we delete each of the pixels on each row by just removing that pixel and moving the rest of the image 1 pixel to the left. So what this will do then is remove that run of pixels. And we have this idea of using dynamic programming to identify seams that we might want to remove. So if we imagine that we are working with a pixel, but with an image that contains just a single row of pixels, then the job would be easy, right? We just measure the value of each pixel and just remove the one that has the lowest value. So in this example, we're going to have two things recorded. We're going to have the actual value of the pixel via this Sabel operation, which is in red, and then we're going to have the cumulative score of all of the seam, of the best seam, ending in that pixel. So in this example, where we've just got one row of pixels in the image, they're both the same thing. But if we consider an image that has two rows of pixels, then what we're going to do is start here, is having computed this, we're going to have the second row of pixels, and we're going to consider which of these pixels we'd move to, such that when we move back along the seam, we sum up to the least amount of pixels. And we do that, again, considering this cumulative score. So in this case, if I want to move from here to here, I have a cumulative score of 1 plus 2 that gives me 3. That's the score for my seam. Okay? So when I'm at this pixel, I look to see which is going to give me the lowest cumulative score. Is it going to be here? Is it going to be here? No, it's this pixel, so I make that connection. If I do that across successive pixels, rows of pixels, I end up forming these seams. Again, looking for the seam that has the lowest aggregate score. So it's a route from the bottom to the top, giving me the lowest score. And that score is reflected by the cumulative score at the bottom of the seam. So it's just an inductive relationship between those rows that gives me that seam. So what we're looking for in this answer then is firstly the identification that this is the seam carving algorithm. Then a brief description of the algorithm that involves how we identify an importance map across the image and how we do this inductive step to identify the best seam to remove. Part 2, the user wants to remove a large object from the photo, e.g. a person standing in front of a building. Which algorithm have we covered on this course that can do that? Unfortunately, it's not Laplacian. No, try again. It's the patch-based inpainting, yeah, the patch-based image completion. Okay, so with the Laplacian inpainting, what we try and do is in the hole of the hole we're trying to fill, we try and fill that hole with pixel values such that there's as smooth as possible a gradient, so as little change as possible within that hole. What that means is if it's a large hole that we fill with that method, we get this kind of unnaturally smooth hole in the image versus the rest of the image which is textured. If we want to fill a large hole, it's better to copy and paste similar bits of texture from elsewhere in the image to fill up that hole, and that's what the Freeman-Efros patch completion method does. Okay? So, well, actually I'll pull up the appropriate slide again. Not sure where that is. Got it. Oh dear. Right. Sorry, then. Causing me problems. Right. So the idea is to have an image with a large hole in it, the hole we want to fill. What we do is we iteratively fill the hole by copying and pasting patches from elsewhere in the image. So for example, I would identify all the pixels around the perimeter of this hole and then iterate around them, doing the following. I would take a window established around that patch and identify the patch elsewhere in the image that has the smallest sum of squared difference between that window and that location in the image, under the valid area of the image, of course. Okay, so I would and I would look at all of the patch locations in the image to identify that best patch, and then I would copy and paste that patch, but paste only the region inside the hole, just within that window. Does that make sense? So in this case, I might discover by differencing this portion of the window established around this particular pixel I'm iterating at, differencing that with every location in the image, I find that this is the best location. I then copy the other part of that window and paste it into the hole in order to perform that filling. And as I iterate around here, I'm taking into account the previous pasted data, so the hole gets filled. And then I basically progressively fill the hole until there's nothing left. Yeah?
How do you determine the size of the patch?
Oh, it's just a constant in your program. You guess it. Yeah. So I don't know if Tu, because Tu gave this lecture while I was on paternity leave, I don't know if he ran the demo in MATLAB, but anyway, it was in your lab code that you would have run it hopefully yourself if you're there. Then you'll see that if you choose patches that are very small, then you get quite a seamless in-paint, but not much texture in the hole, of course. But if you have a patch that is large, you get kind of good texture, but sometimes there's visual continuity artifacts. So you have to get a patch that's just right, and what just right is going to depend really on the scale of the content in your image. Okay. Okay, so that's the exam paper again. Okay, then part 3. The user wants to remove small scratches, e.g. to restore an old photo. Well, okay, what do we use for that? Yes. So, right, how does that work then? Well, again, we have an image with a hole in it. And what we're trying to do is create an in-paint in this hole that is as smooth as possible. What do we mean by as smooth as possible? We mean choosing pixels to fill in that hole to minimize the amount of high-frequency information that's in that hole. How are we going to measure the amount of high frequency in the hole? We're going to convolve the image, well, just that hole actually, with Laplacian, which we remember from the image sharpening lecture, looks like this, 3x3. Okay, and if I run that over my hole that I've in-painted and sum up all the responses from that, that's going to give me a measure for how much high-frequency content is in there. Why? Because this filter, this 3x3 filter, is actually measuring delta f, where f is my image function, like a grayscale function, delta x squared. So it's taking the second derivative with respect to x squared and adding it to the second derivative with respect to y squared. And that is my Laplacian operator. So, how do I find the pixels then that give me an in-paint that minimizes that Laplacian over that region? Well, I solve a linear system. What does the linear system look like? Well, we have a large square matrix called A, which is our design matrix. This matrix contains a row for every pixel in my image, not just the whole, like the whole image, the whole, not just the whole image, the entire image. Okay. The pixels that are known, i.e. the pixels that are not in the hole, are represented by a row that contains just a single 1, and the rest of the row is 0. And the 1 is positioned at the place to encode positive value for the particular pixel. So the convention I usually adopt is if I run through all the pixels in order from top left all the way down to bottom right, number those pixels 1, 2, 3, 4, all the way up to n for the pixel number n. You've got n pixels in that image. Okay, then at location n, that will encode the nth pixel. Yeah. So if this image was entirely known pixels, we would just have a very, very large identity matrix. Yeah? But this, okay, so that's for the known pixels. And what I want then for the known pixels is to come up with a solution, which is what this x vector is. X is the answer we seek, such that that pixel ends up being its original value. So for known pixels, this k1 would be the grayscale value of pixel 1, i.e. the known value of it. Remember, these are values that are not in the hole, so we know their values. Yeah? I'm assuming here a grayscale image. If it was a color image, I'd just do this whole thing 3 times over for the red, green, and blue channel independently. Okay, but let's just pretend it's grayscale image for now. So the known pixels, we want 1 times that pixel to equal its known value, its original value. So if this had no hole in it, and that was a big identity matrix, this would be all my unknowns, and they'd all solve to basically be equal to the k's, which are their known grayscale values. Does that make sense? But of course, the point of doing this is that there are some unknown pixels, which is the pixels in the hole. So what do those rows look like? Well, we create a row for the unknown pixels that has a 4 at the pixel's respective position. So in this case, at 89, 89 in the square matrix, there's a 4. Okay. And then immediately to the left and right of it, we have -1 and -1. And then width pixels to the left and the right of it, we have a -1 and a -1. So that means that the pixels located to the left, the right, the top, and the north, the south, so east, the west, north, the south of that unknown pixel have the values -1 encoded within that row. And the actual pixel's location has the value 4 encoded in it. Okay. What that's encoding, of course, is that Laplacian filter centered at that pixel. And we want that Laplacian to be as low as possible, because that Laplacian has squared terms in it. The lowest it's ever going to be is 0. So we want it to be 0. So when we solve this linear system, which contains now known and unknown pixels, we want the pixels that are known to map to their known values, and we want the Laplacians of the unknown pixels to map to 0. So that's how we form our large linear system. It's of the form AX equals B, so the solution should be X equals A inverse B. However, that means we have to invert an n by n matrix, which is our matrix A, which is likely to be very, very large because it's, there's n pixels in an image. We might be dealing with a megapixel image here. But we observe that A contains a lot of zeros in it, so it's what we call a sparse matrix. So we can use special sparse solvers to solve for X, which we definitely are not going to go into on this course, but are conveniently implemented with the backslash operator in MATLAB. So we use a third-party library to solve that linear system, and we solve it for each channel. So, yeah. So in this example here, with my friend on holiday being deleted from an image, you can see the problem I was describing with the large in-paint, which you wouldn't get with the patch-based in-painting, which I think I probably have an example of later on. So that's the Laplacian in-painting result. And then with the Freeman-Efros, in fact I have a comparison. Okay. Right, any questions on any of that in-painting stuff? Okay. Let's continue on then. Question 4. Okay. Explain with appropriate diagrams how the bag of visual words representation can be trained and used to recognize activities in video. Okay. So we're talking about bag of visual words here, but we're talking about activities in video. Okay, so we're now talking not just about bag of visual words for object recognition, but we're talking about how that framework was extended to perform activity recognition in video. Okay, so let's start by recapping on the bag of visual words representation. The purpose of bag of visual words is to aggregate a whole bunch of sparse features detected over an image into a single image descriptor using a learned dictionary of code words. So if I have, again, this is just starting with object detection. If I have a whole stack of images and I detect sparse features in all of them, so I've got key points in all of them, what I'm going to do is, local to each of those key points, compute a descriptor, something like perhaps a SIFT descriptor or a hog descriptor. And all of those descriptors from all of those images are all going to land up as points in some feature space. Now, if I'm using SIFT, that feature space will be 128 dimensional. So via SIFT, I'm going to get a whole bunch of points, millions of points potentially if I've got a very large number of images here in my data set. Then what I'm going to do is cluster those points. And I'm going to use the k-means algorithm to cluster those points into k clusters. And I will manually choose the k. Usually for object recognition, it'll be about 1,000 or 2,000 will tend to work best, just empirically. So those same data points, I'm just going to start drawing ellipses around them to group them into clusters. The k-means algorithm would do that. For the purposes of this question, we're not being asked about how k-means works, so we can just write k-means. It's only 20%. Okay. This is going to be cluster 1, 2, and there'll be plenty more up to cluster k. Therefore, every feature in here belongs to a cluster. So if that one might belong to cluster 1, that to 2, that to 5, that to 2. So for every image in my data set now, I can make a histogram with bins that go from 1 all the way up to k. And I'm going to just count how many times, how many of each kind of, each cluster of code word I have. And I'm going to normalize that histogram, and then that histogram will be a point in k-dimensional space. That is a descriptor that has been generated by this process, which we call bag of visual words, or sometimes called VQ, vector quantization. Because what we're doing is quantizing this feature space, the SIFT feature space, into k different regions. Okay? So that's the bag of visual words framework as applied to object recognition. That's how we train up the system, by basically doing clustering on this training data. And then if I've got a new image that I want to figure out what its descriptor is, I detect key points, I compute my SIFTs, I look up those locations, figure out which cluster they're nearest to, and I produce a histogram. So I can compute a histogram not only for images in my training set, but also any other image, having done this k-means clustering on my training set. So how does this framework then get adapted from object recognition to activity recognition? Well, actually, the only thing that needs to change is this very first step, which is the feature extraction. Okay? So if we're working on activity recognition in video, we're working with video quantity, then what we will tend to do is consider the video as a space-time cube, which means we consider the frames to have some width and height, x and y, but we have a third dimension, t, which is time. So any pixel now has location x, y, t, where t is its frame number, and x and y are its location in that frame. Okay. Now, when we're working with images for object recognition, the way that we compute features is by computing basically a hog feature local to each of these key points, which involves, again, for 20% we don't need to talk about it, but it involves creating a histogram of the edge orientations in the pixels local to that key point. SIFT is just a particular kind of hog descriptor. When we're working with video, what we tend to do is compute those hogs not just in x and y, but also in t. So we establish a little window that might be, I don't know, 15 by 15 pixels would be typical for hog. Then it would be 15 by 15 by 15 pixels, or voxels, we might want to call them, in the video. It still results in a histogram, which is basically a point in a high-dimensional space, and then the rest of the pipeline continues just as it was. So that would be how we extract hog features, like hog 3D. Sometimes they're referred to features for video. And then the system then is used to extract descriptors that correspond to the activities present in it, which then you would put through an SVM or some classifier in order to do your final detection, just like you would with object recognition. The other thing that we sometimes do, instead of using hog, compute an optical flow field for every frame of the video, and then do the same thing, but then when we're calculating gradients in the space-time cube, we're not calculating them over the grayscale values of that frame, having been pushed through edge detectors and so on. We're calculating them over the optical flow field. We call that HOF, histogram of flow. So just changing the images from actual images to optical flow fields that we've computed for each frame. So there's two ways of doing it, but the answer is draw a diagram of bag of visual words, and then for the feature extraction stage, note that we're extracting space-time features instead of just spatial features. Okay? Right, any questions on that? Right, part B. Consider a video of a textured object moving in 3 dimensions. Sketch and explain how the observed optical flow field might appear under various kinds of motion. So this is really asking you to think about the relationship between the motion of an object in 3D, and it's helping you out here, it's saying it's textured, so there's none of this sort of problems that we're going to see if the object didn't have any texture, where we'd only perceive its motion at the edges. It's a fully textured object, so it's just asking you how, as an object moves in 3D in different ways, how might the optical flow field look? Well, let's imagine it was a textured sphere. If the textured sphere was rotating, what would the optical flow field look like? Well, if it was rotating, say, on its axis like this, then the optical flow field would be quite small near the poles, quite large near the equator, if you like, of the object, and so on. If that object was moving towards you, then, well, you would probably see some vectors moving inwards towards the center as the object appears to shrink in size as it moves towards you, with very little motion here and quite a lot of motion here. The opposite direction if it's moving away from you. And if the object was moving around in space, you'd see kind of uniform translation if it was moving parallel to the image plane. So it's asking for some examples, really, to show that you understand how an optical flow field might look versus how an object is moving. Okay, part C is asking, oh yeah.
So would that assume that the object has any texture in it?
Well, it says consider a video of a textured object, so it will make that assumption, yes. Sketch a design for a deep neural network that combines visual appearance and optical flow data to recognize activities in the video. Right, so now, having asked you in part A to talk about a classical pipeline for doing activity recognition, we're now asking you what a deep learning pipeline would look like for recognizing activities in video. What does that network look like? Does anyone remember? People have done all sorts of networks for this actually, but we've only studied one, the sort of first one, which was due to Simonian and Zisserman in 2014. Yeah.
Is that the one with the flying chairs?
No, it's not. So the flying chairs was a network for estimating optical flow. It was an encoder-decoder network that was trained on synthetic optical flow fields generated in a ray tracer of chairs. Yeah. No, we're not talking here about computing optical flow. We're asking about classifying activities in video, which is different, right? So you might remember that the network was a 2-branch network, where the first branch contained a CNN that dealt with the RGB information, and the second branch contained a CNN that dealt with optical flow data. So in fact, both branches were an AlexNet, but this branch of the AlexNet took in RGB data from time t, from an image at time t, and this took in optical flow data from an image at time t, computed presumably with the image at time t plus 1. So this had 3 channels in it, and this had 2 channels. And then these 2 branches had an AlexNet backbone, and, well, in fact, what they did in this very first paper was they took the softmax classifications from each network and just averaged them. But we could consider that as a special case of learning a fully connected layer that unifies the 2 branches to blend their decisions in an optimal way. So actually a deep network to do activity recognition would have a branch for appearance, branch 1, a second branch for the motion information, and then would have this end stage that unifies the output by adding a couple of additional fully connected layers to give us a softmax output for our activity classes. Does that make sense? Any questions on that? Yeah. So imagine you had an AlexNet you trained up just working over RGB data. You push in a video of someone playing badminton or something, push in a frame of that video, it spits out a decision. You could have a same network that operates on optical flow data, which is a video frame of someone playing badminton that's been pushed through an optical flow algorithm. We don't care what, could be the flying chairs, could be the classical one, it doesn't matter. Okay, that gets pushed through here, we get a decision there too. What we could do is take those 2 decision vectors, as they did in that original paper, and just average them together and to get us an answer. Okay, but that's not ideal, right? Because we don't know what the optimal way is of combining those 2 outputs, and it's a bit arbitrary just engineering a solution which just averages the 2 together. So what we could do instead is create a fully connected layer here that takes as its inputs this and this. So this output was like 1,000 dimensional, this was 1,000 dimensional. We could create a fully connected layer, I don't know, it could have any dimension really. It could also be 1,000 dimensional, yeah? That integrates all of these outputs, into every element within it. Yeah? That's a fully connected layer. Stick a couple of those on the end and have a softmax output which contains an element for every class of activity we're interested in. Okay? And then when we train this network end to end, what we're doing is we're learning the right way to combine the decisions from each of these by training this end stage fully connected layer. Yeah? So that's a kind of an optimal way of doing it, because we're learning, it might be that the best thing to do is to average those 2 vectors together, but it might not, and we'll learn what the right way is from the data, which is the sort of mantra of deep learning, yeah? We don't want to engineer anything in the pipeline, we want to learn all the decisions. Okay, last part then. Last part. Visual question answering VQA systems use text to describe and answer questions about a visual scene. Suggest a network design for VQA system and describe an appropriate methodology for training it. Okay, so actually, for the purposes of time, I won't redraw because it's actually a very similar architecture. What we have with a VQA system, at least one of the initial ones, that has a set of pre-canned answers, is we treat it just like a classification problem. We put the image we want to answer questions about down one branch, which is the CNN branch, and down the second branch, we have an LSTM. And what we'll do is we'll take the sentence of text from a question that we've crowdsourced, take every word in it, and turn it into a word-to-vec vector. So every word turns into a point in a 128-dimensional space. And then we average all those vectors together to produce a single 128-dimensional vector that corresponds to that. Sorry, that's not correct. Let me start again. We take every word in that sentence and turn it into a word net vector, which is 128 dimensional, and then we treat that as a sequence of 128 dimensional vectors which you push through an LSTM. Okay, that will generate two outputs that we then unify through a couple of fully connected layers, just as we did in this example, and end up just in this example with a softmax layer. But this time every element in our softmax output corresponds to a different answer. So I showed you the example, the famous example now, of the girl with the banana moustache. You know, the question was, what fruit, you know, what is the girl's what is the girl's moustache made out of? And the answer, one of the pre-canned 1,000 answers, is banana. Okay, so it's treated as like a classification problem. Does that make sense? So we would, to train such a network, crowdsource a set of questions and answers for a bunch of images. I talked before about how this was done in this initial paper. They collected a set of images. They pushed them out to a crowdsourcing platform like Mechanical Turk to collect questions from users, and then they posed those questions with the image to other users in order to get an answer. And then that was how they collected their triples, if you like, of images and questions and answers. And then they were trained as a classification problem. And then once trained, how can a VQA network be used to answer text-based questions about a scene? Well, you present, having trained this network, you present the network with an image. You present the network with a question, which has been encoded, every word in it encoded via word2vec, and then push through an LSTM to get an embedding out. Push those through your pre-trained, a priori trained, fully connected layers, and you get a classification decision, which is the answer to your question. Make sense? What are the major limitations of typical VQA systems? Yep, you've only got a vocabulary of C classes, or whatever you've chosen C to be. Yeah, basically. How can the VQA network be modified to describe an image of a scene using text rather than respond to specific questions? Okay, so we talked about this. This is where we learn a fact embedding, okay, by encoding let me just get this right. No, actually we don't even have, so we learn a fact embedding by pushing images through here, through the first stage, the first branch of the network, just as we did before. But this time, instead of pushing a question through here during training, we push a natural language description of that image, which has again been crowdsourced, on a Mechanical Turk. So we might have shown images to people and asked them to describe in natural language the image. So there we've got paired input now for training, images with captions basically, which we then present to the network in order to learn these stages and the fully connected layers that unify them. Then we can present an image to the network in order to provoke a point to generate a point in this embedding, and then backpropagate through the LSTM, basically run a decoder through the LSTM in order to generate text, which is generated as points in the word2vec embedding, which then we can convert back into words, the details of which aren't important, but basically it's like a nearest neighbour lookup. Okay, right. So that's the end of then that paper, and also the end of our time. So what we're going to do then is next week we'll continue working through the exam papers. Another exam paper. But what I'm going to do next week is recap on all the areas that you've asked me to before we do that. So if you have taken those revision maps and circled topics that you're interested in me going over again, can I encourage you to just leave them on the side on the way out, and then I'll sort of aggregate them and pick the topics that are most popular. And if you don't want to let go of your revision map to do that, just remember there are plenty of spare copies at the front as well, so don't worry about that. And and remember there is a lab this week as well. It's the last lab. Okay, so I'll see you next week. Thanks very much for your attention.